text has to be turned into a form a model can actually process, and that starts with how we prepare it. The focus here is on the pipeline from raw text to model-ready inputs. The main ideas are text preparation, tokenization, sampling training examples, and turning tokens into vectors. Each of those steps matters because the quality of the input pipeline shapes what the model can learn. Raw documents are not ready for training straight away. They need cleaning, formatting, and structure so the model sees consistent input instead of messy text. The model cannot work directly with whole paragraphs, so the text has to be broken into smaller units. Words and subwords give us a vocabulary the model can learn from while still handling unfamiliar forms. Byte Pair Encoding builds a tokenizer by merging common character sequences into useful subword pieces. That gives a compact vocabulary and helps the model deal with rare words more gracefully. A long text stream has to be cut into overlapping chunks so the model can learn from many next token examples. The sliding window controls how those chunks overlap and how much context each sample includes. Tokens still need numerical representations before they reach the network. Embeddings turn each token into a vector, and those vectors are what the transformer layers actually operate on. A decoder-only transformer predicts the next token from the tokens before it, and that simple objective is what makes large-scale pre-training work. Once the model learns that pattern from huge text collections, it can later be adapted to instructions or specific tasks. The training data must be organized so the model can read it one token at a time and form input-output pairs for prediction. That preparation step is the bridge between raw text and a usable training loop. The diagram separates the full process into stages, and this chapter is centered on the first step of the first stage, building the data sample pipeline. That is the foundation for everything that comes later, because without good samples, the model never sees the right training signal. This part of the workflow sits at the very beginning of LLM coding. Once the sample pipeline works, the rest of training can be built on top of it with much less friction. The lesson connects those pieces into one pipeline. Text becomes tokens, tokens become vectors, and then the data loader produces the examples the model learns from. Each step prepares the next one. So the final training set is structured rather than just a pile of text. Word embeddings solve a basic problem in neural language models. Text has to become numbers before a network can work with it. The point of this part is to show how words turn into vectors and why similar words end up close together. Neural networks rely on arithmetic on continuous values, but words start out as categorical symbols. Embeddings give each word a numeric representation, so the model can compute with language instead of treating words as labels with no structure. If vectors or tensors feel unfamiliar, that background helps with the mechanics, but the main idea here is simpler. Language has to be turned into a format a model can process. An embedding is the mapping itself, and it can come from a learned layer or a pre-trained model. The important part is that different data types need different embedding systems, because a text embedding model does not make sense for audio or video. The diagram groups raw data on one side and vector representations on the other. Track the idea that the input starts in a form a machine cannot directly train on, and the embedding model turns it into a dense numeric vector. That transformation is the core move in deep learning for language and other modalities. Once the data is in vector form, the network can compare, combine, and update it during training. The value of an embedding is not just compression. It is placing related objects into a space where distance and direction carry meaning. That is what makes non-numeric data usable by neural networks. Text can be embedded at different levels, from a single word to a full document. Sentence and paragraph embeddings are useful when the task is retrieval, but for GPT-like models, the main unit is the word, because generation happens one token at a time. Word2Vec made the idea practical by training a model to predict surrounding words from a target word, or the other way around. That training objective pushes words used in similar contexts to land near each other in the embedding space. The clusters matter more than the exact coordinates. Birds gathering near birds and cities gathering near cities show that the geometry is carrying semantic similarity. A two-dimensional plot is only a visual shortcut, but makes the structure easy to see. Nearby points usually reflect words that share meaning or usage patterns, which is the behavior we want from embeddings. The number of dimensions is a trade-off. More dimensions can store finer distinctions, but they also cost more memory and computation, so the choice depends on the task and the model size. Instead of relying only on a pre-trained system like Word2Vec, modern LLMs usually build embeddings into the input layer and update them with the rest of the model. That lets the vectors specialize for the exact training data and objective. Visualization breaks down once the vectors become very large, because our eyes handle only a few dimensions at a time. Even so, models like GPT-2 and GPT-3 use large embedding sizes because that extra capacity can improve performance at the cost of efficiency. The practical pipeline starts with words or subwords, turns them into tokens, and then assigns each token a vector. That sequence is the bridge from raw language to the numeric input an LLM can train on. Tokenizing text is the first step that turns raw writing into pieces a language model can work with. The goal is to split text into words and punctuation, so those pieces can later become embeddings. A token can be a word, but can also be punctuation or another special character. That matters because a model learns from the exact sequence of these pieces, not just from whole sentences. Track the path from raw text to tokens, then to the numerical representations used by the model. The key idea in the figure is that tokenization sits right at the start of the pipeline. This figure places tokenization inside the larger LLM workflow. It shows that the model does not start with words in the human sense. It starts with a cleaned-up stream of tokens. The sample text comes from a public domain short story, so it can be used freely for training experiments. Using a real passage gives us realistic punctuation, capitalization, and dialogue marks to work with. A local copy makes the examples easy to run. Once the text file is on disk, the rest of the processing steps can work directly on it. The URL points to the raw text file, and the last line saves it under a simple local name. This gives us a reproducible file that we can load in the next step. Once the file is available, standard file I/O is enough to read the full story into a string. That string becomes the raw material for tokenization. The next step is a basic read operation. Open the file, read all characters, and inspect a small slice. That quick check tells us the text loaded correctly before we start splitting it apart. The file is opened in text mode with UTF-8 encoding. Then the whole contents are read into raw_text. The print calls confirm the size and show the opening characters so we can verify the sample looks right. A preview is useful because it gives a fast sanity check without flooding the screen. The character count also tells us the rough scale of the sample we are about to tokenize. The output shows both the length of the story and the opening line. That opening line already contains capital letters, dashes, and punctuation, which makes it a good test case for tokenization. The target is a list of words and symbols that can later be mapped to embeddings. Once the text is split into consistent pieces, the model can start learning patterns over those pieces. Real LLM training uses huge collections of text, often many gigabytes. A small story is enough here because the point is to understand the processing steps without needing heavy hardware. Regular expressions give a compact way to describe separators, such as white space or punctuation. The syntax can look unfamiliar at first, so the important part is the result, not memorizing the pattern. A first pass is to split wherever a whitespace character appears. That separates many words, but it still leaves punctuation attached to some of them. The pattern r\s tells Python to split on whitespace and keep the separator as its own item. That is useful here because it lets us see exactly where the breaks occur before refining the rule. The list now exposes the structure of the sentence, but the spaces are still mixed in with the useful pieces. That means the tokenization is only partly finished. The output confirms the split happened at spaces, yet the commas and periods stayed attached to the neighboring words. That is the next thing to fix. Lowercasing everything would throw away useful information, especially names and sentence starts. A better tokenizer preserves case and treats punctuation as its own token so the model can learn both structure and meaning. The pattern expands to include punctuation marks as explicit separators. By naming them in the split rule, words and punctuation can become separate list entries. Now the split pattern catches commas, periods, and whitespace. The parentheses keep those separators in the result, which is why we can still clean them up afterward if needed. The sentence is broken into the pieces we wanted, but the split produces empty strings and spaces as well. Those extra items are harmless to remove. The important result is that commas and periods are no longer attached to words. The leftover blanks are a side effect of how the split expression captures separators. A simple cleanup pass can drop items that are only whitespace. That keeps the token list compact without losing any meaningful content. The list comprehension keeps only items whose strip form is non-empty. In practice, that removes spaces while leaving words and punctuation untouched. At this point, the token list is cleaner and easier to use downstream. Each entry now carries actual text content rather than formatting noise. The cleaned result contains only the words and punctuation marks. That is the shape we want before turning tokens into model inputs. Some applications need spaces preserved, especially when spacing carries meaning, like in code. For this example, removing them keeps the output simpler, but later tokenizers can represent whitespace explicitly when that matters. The first version handles only basic punctuation, so it needs a wider pattern for real text. A better tokenizer should recognize dashes, question marks, quotes, and other special symbols too. The expanded pattern adds several punctuation marks and the double dash as separate split targets. The cleanup line then removes blanks, leaving a token list that handles this more realistic sentence correctly. The printed result confirms that the dash, question mark, and punctuation are all separated properly. That means the rule is flexible enough for this sample sentence. The sequence now preserves the words and isolates the special characters as separate tokens. That is much closer to what a tokenizer should produce for training. The broader pattern succeeds on the tricky punctuation in the story sample. That gives us confidence to apply the same idea to the full text rather than just the toy example. Focus on the separation between ordinary words and the punctuation tokens. The figure's point is that the text is now broken into a small, manageable set of pieces. The figure summarizes the result on the sample sentence. 10 tokens is a tiny example, but makes the splitting rule easy to inspect by eye. With the rule working on a short example, the same logic can now be run over the full story. That reveals how many tokens the complete text contains. The same split and clean pattern is applied to raw underscore text instead of the short example. Printing the length gives the total number of tokens after whitespace is removed. That count tells us how many pieces the story becomes after tokenization. A second quick print of the first few tokens lets us verify that the process is still behaving correctly. Showing the first 30 tokens is a practical spot check. If the beginning looks right, the same rule is likely working throughout the rest of the text too. The preview shows words, capital letters, and punctuation each in their own place. That is the sign that the tokenizer is splitting the story in a consistent way. The opening tokens preserve the original capitalization and separate the double dashes and comma cleanly. That gives us a usable token stream for the next step, where these tokens can be mapped into model-friendly representations. Tokens become useful for a model only after each one is assigned a stable integer ID. That integer form is the bridge from raw text to embeddings and, later, to everything the model computes. The conversion to integers gives every token a machine-friendly label. Those labels are not the final representation, but they are the necessary step before the model can look them up in an embedding table. A vocabulary is the lookup table that makes the mapping possible. Each unique token gets one unique integer, and that one-to-one mapping is what lets us turn text into IDs consistently. The figure groups the process into a simple idea. Collect the distinct tokens, sort them, remove duplicates, and assign an ID to each one. The exact token list matters because the same vocabulary has to be used whenever text is encoded later. The important part is the mapping, not the size of this toy example. A real vocabulary usually contains punctuation and special symbols too, but the structure is the same: token in, integer out. Once the text has been tokenized, the first step is to deduplicate it and sort it. That gives a repeatable ordering, which is important because the token IDs should not change every time you run the code. The set removes repeats, sorted give a fixed order, and len counts how many unique tokens there are. That count becomes the vocabulary size, which tells us how many entries the lookup table must contain. That number tells us how many distinct tokens appear in the training text. From there, we can assign an ID to each token and inspect the first part of the mapping to make sure it looks right. The next step is to turn the sorted token list into a dictionary. That dictionary is the actual vocabulary the tokenizer will use for encoding and decoding. Enumerate gives each token its integer label in order, and the dictionary stores that label beside the token. Printing only the first 51 items keeps the output short while still showing the pattern of the mapping. The printed pairs confirm that each token now has one fixed integer ID. That exact pairing is what lets the tokenizer move between text and numbers without guessing. The output shows the dictionary in action, a token on the left and its integer on the right. The specific numbers do not matter. What matters is that the same token always resolves to the same ID. Once the lookup table exists, new text can be tokenized and converted into IDs in one pass. The same vocabulary also lets us reverse the process later, which is essential when we want to turn model output back into readable text. The diagram is showing a two-step path. First, split the new sentence into tokens, then use the vocabulary to replace each token with its integer label. That same vocabulary can be reused on the training text and on any later sample, as long as the tokens exist in it. The important idea is reuse. A vocabulary built from training data becomes the shared codebook for every encoding step, so the model sees text in a consistent numerical form. Encoding alone is not enough because model outputs are also integers. To read them again, we need the reverse mapping from ID back to token, so the numerical sequence can be turned into text. A tokenizer usually exposes both directions. One method splits text and maps it to IDs, and the other takes IDs and reconstructs text from the inverse lookup. The class ties the whole process together. It stores the vocabulary once, then uses it for both encoding and decoding so the mapping stays consistent across calls. The constructor keeps both directions of the vocabulary, string to integer and integer to string. Encoding splits the input with a regular expression, drops empty pieces, and looks up each token. Decoding does the reverse, and then fixes spacing before punctuation so the text reads naturally. Those comments mark the core mechanics. The first two lines build the two lookup tables. The third and fourth methods handle the forward and backward conversions, and the last line cleans up the text after joining tokens with spaces. With the class defined, a tokenizer object can be created from any existing vocabulary. That gives us a reusable tool for turning text into IDs and IDs back into text. The figure links the two directions of the class. Encode takes text apart and maps it forward, while decode rebuilds the text from the IDs. Keeping both methods in one object makes the vocabulary available to both steps. The diagram reinforces the full round trip. Text becomes IDs for the model, and IDs can be turned back into text whenever we need to inspect or display the result. A quick test with real text shows whether the vocabulary and splitting rules are working together. The example passage comes from the training data, so every token should already be known to the tokenizer. The tokenizer is built from the vocabulary, then used to encode a short passage. Because the text comes from the same training source, every token can be matched to an ID without trouble. Those numbers are the model-facing version of the passage. Each one stands for a token from the vocabulary, in the same order as the text appears. The list confirms that every token was converted into an integer ID. Nothing about the numbers is special by itself. Their value comes from the vocabulary mapping that produced them. The reverse step checks whether decoding works just as reliably as encoding. If the inverse vocabulary is correct, the original passage should come back in readable form. This call sends the integer sequence through the inverse lookup and rebuilds the text. The spacing cleanup at the end is what keeps punctuation attached in a natural way. The results should match the passage closely, apart from small formatting artifacts introduced by the simple tokenizer. That confirms the encode-decode cycle is working. The reconstructed text lands back near the original sentence, which shows that the ID sequence preserved the token order. A simple tokenizer can round-trip known text, even if its spacing rules are still rough around punctuation and contractions. That round trip is the goal. Numbers in one direction, text in the other. Once both mappings exist, the tokenizer becomes a reliable interface between language and the model. A tokenizer also has to face new input, not just memorize passages. That test tells us whether the vocabulary is broad enough to handle text outside the training example. This input contains words that were not part of the story vocabulary. Encoding will fail as soon as the tokenizer reaches a token it cannot find in the dictionary. The failure is the point. The tokenizer can only encode tokens that exist in its vocabulary. If a word was never seen during vocabulary building, there is no ID available for it. The error pinpoints the problem token. Hello is absent from the vocabulary, so the lookup fails immediately instead of producing an ID. That limitation comes from the training text. If a word never appeared there, the tokenizer cannot assign it an ID. A larger and more diverse training set reduces this problem, which is one reason vocabulary design matters so much for LLMs. The next step is to deal with unknown tokens more gracefully and introduce special symbols that give the model extra structure during training. Those additions make the tokenizer more practical when the input goes beyond the original dataset. Special tokens give the tokenizer a way to mark unknown words and document boundaries, and that matters whenever text comes from more than one source. These markers help the model keep track of what belongs together and what should be treated as separate. A tokenizer needs a fallback for words it has never seen, and it also needs a boundary marker when unrelated texts are joined together. Adding these tokens makes the vocabulary more practical for real training data, where missing words and multiple documents are normal. Focus on the two roles in the figure. One token stands for unknown words, and the other marks where one text segment ends and another begins. That separation is important because the model should not assume unrelated passages form one continuous story. The vocabulary grows by a small amount, but the behavior changes in a big way. Now, the tokenizer can represent words it cannot match. It can also mark transitions between independent text sources. When a word is outside the vocabulary, the tokenizer substitutes the unknown token instead of failing. The boundary token is just as important during training on books or documents because it tells the model that concatenated text is still made of separate pieces. The key idea is that the model sees one continuous stream, but we add a marker so it can learn where one source stops and the next begins. That keeps the training signal cleaner when the input comes from different books or articles. That marker functions like a boundary flag. It tells the model that the neighboring text should not be blended together conceptually, even if it appears next in the training sequence. The implementation starts by extending the list of unique tokens with the two special symbols. Once they are part of the vocabulary, the tokenizer can map them to IDs just like any other token. The first line collects the unique words, and the next line appends the two special tokens. After that, the vocabulary dictionary assigns each token its integer ID, and the print statement checks that the size increased by 2. That count confirms the extra tokens were added successfully. The increase from 1,130 to 1,132 matches the two new entries we inserted. A quick inspection at the end of the dictionary is a useful sanity check. If the special tokens appear there, the vocabulary update worked the way we expected. This slice takes the last 5 vocabulary entries and prints them in order. It is a simple way to verify that the new symbols were appended to the mapping. What matters here is that the vocabulary ends with the ordinary words followed by the two new markers. That placement makes it easy to confirm that the mapping includes the unknown word token and the end of text token. The output shows the two special tokens at the end of the ID list. Their IDs are now part of the vocabulary, so the tokenizer can omit them whenever it needs a boundary marker or an unknown word fallback. That confirms the vocabulary change, and the tokenizer can now be updated to use those IDs during encoding and decoding. The next version is the same basic tokenizer, but with a missing word fallback built in. The tokenizer now has a fallback path for out-of-vocabulary words, which keeps encoding from breaking on unseen text. The important part is not the class name, but the way it preserves a usable token stream, even when the input is imperfect. The constructor stores both directions of the vocabulary, so encoding and decoding can move back and forth cleanly. In encode, the split and strip steps isolate words and punctuation, then the unknown word line swaps in UNC whenever a token is missing. In decode, the join step rebuilds the text, and the regular expression removes extra spaces before punctuation, so the result reads naturally. Those two notes point to the only behavior changes that really matter. One protects the tokenizer from unseen words, and the other keeps decoded text from looking awkward around commas and periods. Compared with the earlier tokenizer, the main improvement is resilience. Instead of stopping when a word is missing, it records the unknown token and keeps the sequence intact. A good test is to combine two short sentences that have nothing to do with each other. That makes the separator token visible in the token stream and shows why the model needs it during training. The two strings are independent, and the join inserts the end of text marker between them. That creates one training sample that still preserves the boundary between the two original sources. The printed line confirms that the separator sits between the sentences exactly where the model needs it. Nothing about the original text is lost. The boundary is just made explicit. The output shows both sentences with the boundary token in the middle. That marker is what lets the model see two independent passages inside one stream of training text. Now the sample is ready to pass through the updated tokenizer. This step reveals both how unknown words are handled and how the separator token survives encoding. The tokenizer is built from the updated vocabulary, then used to convert the text into integer IDs. The result should include one ID for the separator and fallback IDs wherever the vocabulary does not contain a word. The ID list is the real test of the tokenizer. It shows whether the special boundary token and the unknown word token were inserted at the right places. Two positions use 1131, which means two words were not in the vocabulary and were replaced by UNC. The 1130 in the middle marks the boundary between the two text sources. That pattern is exactly what we wanted to see. The tokenizer is no longer fragile, and it can represent both unseen words and document boundaries in a consistent way. A round trip through encode and decode should preserve the structure of the text, even if unknown words are replaced. The check tells us whether the tokenizer is behaving consistently. Encoding followed by decoding tests both directions of the mapping at once. If the tokenizer is correct, the output will keep the separator and turn missing words into the unknown token instead of crashing. The decoded text should still be readable, but words outside the vocabulary now appear as UNC. That makes the missing vocabulary visible instead of hiding it. The two unknown words have been replaced, while the separator token remains in place. That shows the tokenizer can recover a valid text form even when the original words were not known. Those replacements tell us something about the source text. The training corpus did not include those words. The tokenizer is exposing the limits of the vocabulary rather than pretending every word is known. Different training setups sometimes need a few more markers than just unknown words and text boundaries. The common ones are about sequence starts, sequence ends, and padding for batches of different lengths. A beginning of sequence token tells the model where content starts. That can be useful when the model needs an explicit signal before the first word appears. An end of sequence token marks where one sample stops. It becomes especially helpful when multiple unrelated texts are packed together, because the model can see the boundary clearly. Padding solves a batch shape problem. When examples have different lengths, the shorter ones are extended so every item in the batch lines up with the same number of tokens. For GPT-style models, a single end-of-text token is enough for both sequence boundaries and padding. During batch training, masking removes padded positions from attention, so the exact padding token stops matching. GPT avoids a separate unknown token by using byte pair encoding instead. That tokenizer breaks words into subword pieces, so even unfamiliar words can usually be represented without giving up on the input. Byte pair encoding is a stronger way to break text into tokens. And it matters because this is the scheme behind the tokenizers used by GPT-2, GPT-3, and the original ChatGPT model. BPE starts from small pieces and builds up a vocabulary from frequent patterns in text. That makes it compact, efficient, and much better at handling real-world language than a simple word list. Rather than implementing the algorithm from scratch, it is practical to use TikToken. It is a Python library with a fast Rust backend, so it gives us the same BP behavior without the implementation burden. Installing the library is straightforward from a terminal. Once that package is available, the tokenizer tools are ready to use in Python. Version checks matter because tokenization behavior can change between releases. Using the same version keeps the token IDs and decoding behavior aligned with the examples. The first import reads package metadata, and the second imports the tokenizer library itself. Printing the version tells you exactly which release is installed before you run any tokenization code. Once the library is installed, you create a tokenizer by asking for a named encoding. The GPT-2 encoding is a standard BP vocabulary that we can use to encode and decode text. This line loads the GPT-2 tokenizer object. After that, the tokenizer knows the vocabulary and merge rules needed to turn text into token IDs. The interface should feel familiar. Text goes in through encode, and token IDs come back out through decode. The difference is that BP has a much richer vocabulary and can represent far more kinds of text. The input mixes ordinary words, a special end-of-text marker, and an unfamiliar compound word. Allowing the special token tells the tokenizer to keep that marker intact instead of splitting it apart. Those integers are the vocabulary IDs assigned to each piece of the input string. Short common pieces often get compact IDs, while special tokens and rarer pieces get their own entries. These numbers show the exact BPE decomposition chosen for the text. The special token has its own large ID, and the unfamiliar word is broken into smaller pieces rather than rejected. Encoding is only half of the story. Decoding reconstructs readable text from the token sequence. That round trip is what lets the tokenizer serve both training and generation workflows. The decode call reverses the integer sequence into a string. If the tokenizer is working correctly, the reconstructed text should match the original input closely, including the special marker. The printed string confirms that the token IDs can be turned back into readable text. That is the practical guarantee we want from a tokenizer, a stable mapping in both directions. The output keeps the special token and reconstructs the unknown word without loss of meaning. A small spacing difference can appear, but the important point is that the tokenizer preserves the text content through encode and decode. One thing to notice is that the end-of-text marker sits at the top of the vocabulary, with ID 50256. That tells you the GPT-2 vocabulary contains 50,257 symbols in total, including that special marker. The other important point is that BPE does not need an unknown token bucket. When a word is unfamiliar, it falls back to subwords or even characters, so the tokenizer can still represent it. That fallback is the key idea behind BP. A new word is not a dead end. It becomes a sequence of smaller units that the model already knows, which is why the system can process arbitrary text. Focus on the way the unknown word is split into pieces instead of being replaced by a single placeholder. The figure is showing a hierarchy from larger chunks down to subwords and individual characters. The figure makes the fallback path concrete. As the vocabulary runs out of whole word matches, it continues with smaller units. That is why BPE can cover words it never saw during training. That character-level fallback matters for the language model too, because the model receives token sequences even when the raw input contains unfamiliar words. No part of the text is forced into an unknown placeholder. A good test of the tokenizer is to feed it a made-up word and inspect the pieces it chooses. That reveals the fallback behavior very clearly. Tokenizing a strange input like that shows how BP splits it into manageable units. Decoding each integer separately exposes the mapping, and decoding the full list checks whether the original string can be reconstructed. The algorithm starts with individual characters, then repeatedly merges pairs that appear often together. Over time, frequent fragments become subwords and common subwords become whole words, with frequency deciding which merges are kept. A sliding window turns one long token sequence into many training examples. That matters because an LLM learns by seeing short context blocks and predicting the next token after each one. The training data has to be organized into pairs, the context on the left and the next token on the right. Pre-training works by repeating that prediction task across the whole text. The important idea in the figure is the shift by one position. Words before the target stay visible to the model, while anything beyond the target is masked out during training. That setup makes the prediction task local. Each short block becomes one training case. Tokenization still happens first, because the model works with token IDs rather than raw words. The simplest way to build those pairs is to tokenize the entire story once, then take short spans from that token stream. From there, the input and target sequences can be formed by shifting the window by one token. The file is read as plain text. Then the tokenizer converts the whole story into token IDs. Printing the length tells us how many training tokens we have available before we start slicing them into examples. That number is the total token count after BPE tokenization. It gives a sense of the dataset size that the sliding window will sample from. Dropping the first few tokens is just for demonstration, so the sample text starts at a more interesting spot. The sampling method stays the same, only the visible passage changes. This slice keeps everything from token 50 onward. It gives us a shorter sample to inspect without changing the logic of the data loader. For next token prediction, the target sequence is just the input sequence moved one step to the right. That alignment lets the model learn to predict each token from the tokens that came before it. The context size sets the window length. The first slice becomes the input, and the second slice starts one token later. So every position in X lines up with the next token in Y. A larger context gives the model more history to work with. A smaller one is easier to show on the board, but it gives the model less information when it predicts the next token. The printed values make the shift visible. The two sequences are almost the same, except that the target sequence is advanced by one position. The target starts with the second token from X, then continues forward. That pattern is exactly what the model is trained to reproduce at every step. Each context-to-target pair becomes one tiny language model task. Feed in the left side and ask the model to assign high probability to the token on the right. This loop grows the context one token at a time and pairs it with the next token. That makes the prediction problem easy to see. Every longer prefix points to one desired continuation. Each line is one more step in the same prediction chain. The model sees a prefix, and the training target is the token that completes it. The output shows the prefix getting longer while the target keeps moving forward. That is the exact structure the model learns from: a growing context and one next token to predict. The left side is what the model receives, and the right side is the token it should predict. Converting those IDs back to text makes the training objective much easier to read. Decoding the IDs turns the numerical examples back into words. That helps confirm that the token shift is the same whether we look at integers or text. The text version removes the distraction of raw IDs. What matters is the same structure: a growing prompt on the left and the next word on the right. The words read like a normal sentence fragment, which is exactly the point. The model is not memorizing whole sentences. It is learning to continue them one token at a time. At this point, the core training examples are built. The only thing left is to package them efficiently so PyTorch can feed batches to the model. An efficient loader should return two tensors, one for the model input and one for the shifted targets. The code will work directly with token IDs because tokenization and ID conversion happen together in the encoder. The key relationship in the figure is row by row. Each row in X is one context, and the matching row in Y is the next token target for that same context. That pairing is what batching needs to preserve. The two tensors carry the same examples in a line form. One tensor feeds the model, and the other gives the correct continuation for each row. PyTorch already has the right tools for this pattern. A dataset defines how examples are indexed, and a data loader groups those examples into batches for training. The dataset class sets up the sampling logic. Once that is in place, batching the data becomes a small wrapper around it. The dataset class packages overlapping token windows into rows that PyTorch can index. Each row will later become one input target pair for training. The constructor tokenizes the whole text once, then walks through token IDs with a sliding window. Each window produces an input chunk and a target chunk shifted by one token, while underscore underscore, length underscore underscore, and underscore underscore, guidem underscore make the class behave like a normal PyTorch dataset. Those notes describe the whole mechanism in 4 pieces. First, the text is tokenized, then the window moves through it, and finally the dataset exposes its size and individual examples to PyTorch. Each stored row holds one context window and its matching prediction targets. The important idea is that the class precomputes those rows so the loader can read them efficiently later. If those classes are new, it helps to think of dataset as the source of examples and data loader as the mechanism that feeds them in batches. The same pattern appears in many PyTorch training loops. Once the dataset knows how to produce examples, the data loader can handle batching, shuffling, and iteration. That separation keeps the data pipeline clean. The loader is just the bridge between raw text examples and training batches. It wires the tokenizer, dataset, and data loader together into one function. The function creates a GPT tokenizer, builds the dataset from the text, and then wraps it in a data loader. The batch settings control how examples are grouped, whether they are shuffled, and whether a short last batch gets dropped. Each annotation points to one part of the pipeline. The most practical detail is drop underscore last, because uneven batches can make training behave inconsistently near the end of an epoch. Using a tiny batch size makes the mechanics easy to inspect. With one row per batch, it becomes clear how the dataset windows and the loader output line up. The text is loaded, then the data loader is created with a very small window and stride, so the overlap is easy to see. Converting it to an iterator, let's next pull one batch at a time from the loader. That line gives direct access to the stream of batches. From there, next can fetch the first example immediately. The printed batch will show two tensors, one for inputs and one for targets. Because the batch size is 1, the shapes are easy to read. The first tensor holds the input sequence, and the second tensor is the same sequence shifted by one token. That shift is exactly the prediction target for next word training. The batch contains both sides of the training pair, and each side has 4 token IDs because the context length is 4. Real language model training usually uses much longer contexts, often 256 or more tokens. A stride of 1 creates the densest overlap possible between consecutive batches. That makes the sliding window behavior easy to inspect before trying larger step sizes. Fetching a second batch shows whether the window actually moved forward. With stride set to 1, the new batch should reuse most of the same tokens and advance by a single position. The comparison with the first batch is what matters. It reveals the one token shift that the stride setting creates. The second batch starts with the first batch moved forward by one token. That overlap is the sliding window in action. Comparing the batches makes the rule clear. The stride determines the step size of the window. A stride of 1 gives maximum overlap, while a larger stride reduces overlap and moves faster through the text. The key parts to track are the window position and how much it advances each time. If the stride matches the window size, the batches do not overlap. If it is smaller, they share tokens. The figure makes the batch movement concrete. It also shows the other extreme, where a stride equal to the window size removes overlap completely. Changing the context size or stride is the fastest way to build intuition. Small settings make the pattern visible, and larger settings show how the same code scales up. Those two settings show very different sampling behavior. One creates short, non-overlapping snippets, and the other keeps a larger context while still moving forward in steps of two. Batch size is a trade-off. Smaller batches are cheaper in memory, but the gradient updates vary more from batch to batch, so training can look less stable. Once the mechanics are clear, larger batches show how multiple examples are packed together. That is the form the training loop usually wants. This version uses batch size 8 and a stride equal to the window size, so each row moves through the text without overlapping the next. The printed inputs and targets show 8 aligned training examples at once. Now the batch contains several rows, not just one. That makes it easier to see how the dataset fills a mini batch for training. Each row in targets is the same row in inputs shifted forward by one token. Using a stride of 4 avoids overlap here, so the batch covers the text more evenly. A stride equal to the window length uses the text efficiently and avoids repeated tokens across neighboring batches. Less overlap also reduces the chance that the model keeps seeing nearly the same example again and again. Token IDs still need one more step before they can enter a neural network. They must become dense vectors. That conversion gives the model a learned representation for each token, which training will adjust over time. The embedding layer starts with random weights, and those weights are the parameters the model learns. Each token ID simply selects one row from that matrix. So the network begins with a vector for every token and improves those vectors during training. The figure connects the 3 stages. Text first becomes tokens, tokens become IDs, and IDs become vectors. That last step is what makes the input usable for gradient-based learning. The important idea in the figure is the final conversion step. The earlier stages create discrete IDs, but the embedding layer turns those IDs into continuous values the model can work with. Backpropagation works with numbers that can change smoothly, not with raw symbolic IDs. An embedding gives each token a vector in a space where the training process can nudge meaning and similarity in useful directions. The training machinery matters here because embeddings are not fixed lookup tables forever. They are ordinary learnable parameters, and backpropagation is the mechanism that updates them. A small example makes the lookup process easier to see. 4 token IDs will be turned into 4 vectors, 1 vector per token position. These are the 4 token IDs that will index into the embedding table. The embedding layer does not invent new values here. It retrieves the row assigned to each ID. The toy setup uses only 6 tokens and 3 embedding dimensions, so the matrix stays small enough to inspect. In a real model, both numbers are much larger, but the mechanism is exactly the same. These 2 values define the shape of the embedding matrix. 6 rows cover the vocabulary, and 3 columns give each token a 3-dimensional representation. A fixed seed makes the random initialization repeatable, which is useful for matching the printed values to the explanation. The layer then creates 1 trainable vector for every token in the vocabulary. The first line fixes the random numbers, the second builds the lookup table, and the third exposes the underlying matrix. What matters is that the layer stores 1 row per token and learns those rows during training. That printed object is not just a collection of numbers. It is the parameter matrix the model will optimize, and each row stands for 1 token in the vocabulary. The matrix starts with small random values and requires underscored rad equals true tells us those values will be updated by training. The 6 rows match the 6 vocabulary items, and the 3 columns are the 3 embedding dimensions. That shape is the key structure to keep in mind. A token ID chooses a row, and that row becomes the token's embedding vector. A single ID should map to a single row from the matrix. That makes it easy to verify the lookup behavior before we pass in a whole sequence. Token ID 3 is used as an index into the embedding matrix. The layer returns the vector stored in row 3, wrapped in a 1-row tensor because the input contains 1 ID. The result should match 1 row from the earlier matrix exactly. That match confirms the embedding layer is performing a direct table lookup. These numbers are the same as row 3 of the weight matrix. The gradient function attached to the tensor shows that this lookup still participates in training. Python uses zero-based indexing, so ID 3 points to the 4th row. That is why the retrieved vector matches the fourth row exactly, with no extra computation beyond the lookup. The same result could be built by turning the token into a one-hot vector and multiplying by a weight matrix. The embedding layer packages that idea into a faster, cleaner operation that still learns through backpropagation. The same indexing rule works for a sequence, not just a single token. Each ID selects one row, and the four selected rows stack into an output matrix. The layer now processes the full tensor of IDs at once. Each element is mapped to its row, and the rows are collected in the same order as the input sequence. Four input tokens produce four embedding vectors, each with 3 numbers. The output shape is therefore sequence length by embedding dimension. Each row comes from one token ID in the input sequence. The order of the rows follows the order of the IDs, so the sequence structure is preserved while the tokens are converted into vectors. That output matrix is just the embedding table sampled row by row. Once the model has these vectors, it can continue with positional information and the rest of the network. Track one token ID across the arrow into the matrix, then follow the matching row back out. The diagram ties the input sequence to the specific rows that become embedding vectors. The point of the figure is the row selection rule. A token ID is an index, and the embedding layer returns the row at that index. Token embeddings alone do not tell the model where a token appears in the sequence. The next step is to add position information so the network can distinguish the first token from the third, even if the token text is the same. Token embeddings alone do not tell a language model where a word sits in a sentence. The missing piece is position, because order changes meaning and the attention mechanism does not know it by itself. A token embedding maps the same token ID to the same vector every time, no matter where that token appears. That consistency is useful, but it also means the model needs another signal if it is going to tell the difference between a word at the beginning and the same word near the end. The important pattern in the figure is that the embedding table only depends on the token ID. Position is ignored at this stage, so identical IDs land on identical vectors even when their sequence locations differ. That makes the limitation concrete. The embedding layer gives you meaning for a token, but not its place in the sequence. The next step is to add position information on top of that representation. Deterministic token embeddings help with reproducibility, but they leave the model blind to order. Adding positional information fixes that blind spot and gives the network a way to tell one occurrence from another. Absolute positional embeddings mark a token's exact slot in the sequence. Relative positional embeddings focus on distance between tokens, which often helps the model handle sequences of different lengths more gracefully. The diagram should be read as two vectors being combined for each token, one for the token identity and one for its position. Both vectors need the same size because addition only works cleanly when the dimensions match. That addition is the core idea behind absolute positional embeddings. Each position gets its own learned vector, and the model uses the sum as the final input representation. Relative position focuses on how far apart two tokens are instead of where they sit absolutely. That makes the representation more flexible, especially when the model sees lengths during inference that differ from the lengths used in training. Both approaches serve the same purpose. They help the model understand order and token relationships more accurately. The choice depends on the architecture and on the kind of sequences the model has to handle. GPT-style models learn absolute position vectors during training rather than using a fixed formula. That means the position embeddings become part of the model's learned parameters, just like the token embeddings. A realistic embedding size makes the vectors rich enough to carry useful information while still being manageable for experiments. The vocabulary is fixed by the tokenizer, and the embedding layer turns each token ID into a 256-dimensional vector. The first line sets the vocabulary size, and the second line sets the vector width. The embedding layer then creates a lookup table with 50,257 rows and 256 columns, one learned vector for each token ID. After the lookup, each token in each sample becomes a 256-dimensional vector. With 8 samples and 4 tokens per sample, the tensor grows from simple IDs into a 3-dimensional batch of embeddings. To see the shape in practice, the next step is to pull one batch from the data loader that give a concrete set of token IDs to embed. This creates batches of 8 sequences, each exactly 4 tokens long, and keeps the sampling order fixed. The printed shape confirms the input matrix is 8 by 4, which is the starting point before any embedding lookup happens. That printed shape tells us the loader is giving 8 short text samples at once. Each row is one sample, and each column is one token position inside that sample. The numeric IDs are just the tokenizer's compact labels for words or subwords. The shape line matters most here, because it confirms that each batch element has 4 token positions to embed. That 8 by 4 layout is the bridge from raw token IDs to model inputs. Once the IDs are embedded, each of those positions will carry a learned vector instead of a single integer. Now the embedding layer can transform the integer IDs into dense vectors. The important change is not the numbers themselves, but the representation they point to. This line applies the lookup table to every token in the batch. The result keeps the batch and sequence dimensions, but each token position now holds a 256-dimensional vector instead of a single ID. The print statement checks that the transformation worked. Shape is the quickest way to verify that the model now has a vector for every token in every position. That shape means 8 sequences, 4 positions each, and 256 features per position. The third dimension is the embedding width, so every token is now represented by a full vector. The output tensor is the token content representation for the whole batch. It still has the original batch structure, but every integer ID has been replaced by a learned vector. For absolute position encoding, the positional vectors must live in the same space as the token vectors. That way, the two can be added element by element without changing the batch shape. The first line sets the number of supported positions, and the embedding layer creates one vector per position. Feeding in a range gives the position 0 through context_length -1, and the printed shape shows one 256-dimensional vector for each slot. The arrange vector is just a placeholder for the sequence positions. If a text is longer than the supported context length, the extra tokens have to be cut off because the model only has embeddings for the positions it was built to handle. The printout confirms that the position layer produces one vector per slot. That gives the model a learned code for where each token sits in the sequence. Four positions times 256 features means the layer is ready to align with the token embeddings. Each row corresponds to a specific position in the sequence. Because the position tensor is 4 by 256, it lines up with each sequence in the batch. PyTorch broadcasts that positional matrix across the 8 samples, so every sample receives the same position pattern. This addition combines content and position into a single representation. The shape stays the same, which is exactly what we want: richer information without changing the interface to the next layers. The check is important because the model still expects a batch of the same shape, just with more information inside each vector. Addition gives that extra information while preserving the tensor structure. The shape remains 8 by 4 by 256 after the position vectors are added. What changed is the meaning of each vector. It now carries both the token identity and its location in the sequence. At this point, the model has the full input representation it needs. Token meaning and position are merged into one tensor, which can then flow into the main transformer blocks. Follow the flow in the figure from left to right. Text is tokenized, token IDs are mapped to vectors, and position vectors are added before the result enters the model. That pipeline is the standard entry point for a GPT-style network. The full pipeline matters because it shows where order enters the system. Without that positional step, the model would only see bags of token vectors rather than sequences with structure. Embeddings, tokenization, and positional information are the pieces that turn raw text into something a language model can actually work with. The rest of the lesson ties those pieces together into one pipeline. Raw text has to become numbers before a neural network can use it. Embeddings place words or other discrete items into a continuous vector space, so the model can compare them and learn patterns with normal matrix operations. That process starts by splitting text into tokens, which may be whole words, subwords, or even characters. Each token is then mapped to an integer ID, giving the model a fixed numeric label for every piece of the input. Special tokens give the tokenizer extra control over unusual cases. An unknown word can be marked with a dedicated symbol, and a boundary token can tell the model where one unrelated text ends and another begins. Byte pair encoding handles rare or unseen words by falling back to smaller pieces. Instead of failing on a new word, it can represent it with subword units or characters that the model already knows. Training data is built by shifting a window across the token sequence. One chunk becomes the input, and the next token sequence becomes the target. So the model learns to predict what comes next. An embedding layer works like a table lookup. A token ID goes in, and its vector comes out. Those vectors are the learned continuous representations that make deep learning on text possible. Token vectors alone do not say where a word appears in a sequence, so position has to be added separately. GPT-style models use absolute positional embeddings, which are learned during training and added directly to the token embeddings.